Welcome to Maths with EJD. We're still talking about partial differential equations and numerical solutions. Uh, Numerical methods for solving them. We have seen the idea of finite difference methods, finite, finite difference methods. We have also considered finite element method. And in this video, we'll be talking about the spectral methods. So, for the sake, okay, of course, this is done. Now we're going for spectral methods. So, spectral methods for solving partial differential equations. So the spectral method is a numerical technique for solving PDEs by expanding the solution in terms of a series of basis functions. Okay. Now, basis functions, these basis functions are often eigenfunctions. They are often eigenfunctions of differential operators, differential operators such as Fourier series, Fourier series, Legendre polynomials, or Chebyshev polynomials. I've touched on some of these at various points. Chebyshev polynomials. Okay. Spectral methods are particularly useful for problems where the solution is smooth. The solution is smooth and can be well approximated and can be well approximated by a finite number of basis functions. Okay, now let's talk about some general steps. General steps. Okay, so general steps for spectral methods. So the first thing we want to do is to discretize the domain. I mean, this has been like a regular pattern for across the methods, right? So the first thing is to discretize the domain. So you define the computational domain and choose an approximate set of basis functions. Common choices include Fourier basis for periodic problems. So maybe I can just itemize. First, you define define the computational domain. Define the computational domain. Having done that, choose appropriate set of basis functions. So you can have some of these choices right here. Say you can have Fourier basis for periodic problems. If you have periodic problems, so it's Fourier periodic problems. Fourier is very good with periodicity. Then you can choose for periodic problems on a finite interval, right? That's for Fourier. For periodic problems on a finite interval, then you can choose Legendre polynomials for problems. So these are for problems on a finite interval with specified boundary conditions. With specified boundary conditions. Okay. So that's the very first step. And the second step is to express the solution as a series. Express the solution as a series. So you approximate the solution as a finite sum of these basis functions. So where you have u of xt approximately summation from n equals 0 to big N of un cap of t phi n of x. So you have space and time well captured here. So with that done, we have approximated the solution of the finite sum of these basis functions, right? Then you now substitute into the PDE 3, substitute into the PDE. So here now you plug the series expansion into the PDE and use the orthogonality. Of the basis functions to separate terms leading to a system of ODEs for the coefficients un cap of t. And then finally, you solve for the coefficients. That's number 4, I believe. 4, solve for the coefficients. So here you solve the resulting system of ordinary differential equations to obtain the time evolution of the coefficients un cap of t, like that. So with that done, let's move on to talk about the example. So in this example, we'll be solving the heat equation using Fourier series. So consider the heat equation in one dimension with fixed boundary conditions. So that's partial u x comma t, partial u of x comma t, partial t equals partial squared u of x comma t, partial x squared. And then we have the domain 0 is less than x is less than L, with u of 0t equals u of L comma t equals 0. Okay. That means the temperature at the beginning of the rod and at the end of the rod, I mean, if you're considering a metal rod, the temperature at the beginning and the end will be 0. So imagine that you are heating it from the center. So let's go for step 1 in this situation. Step 1, we have the Fourier series expansion. Since Fourier is our basis, Fourier series expansion, we could have used Chebyshev or Legendre or anything, but we're using Fourier here. So we express the solution u of x comma t as a Fourier sine series. I have a playlist on Fourier series, so you want to check that out in case this is new to you. As a Fourier sine series, which is u x comma t equals summation from n equals 1 to infinity of un cap of t sine n pi x divided by L, which is the length of the rod, right? That's step 1. That's Fourier series for that. Then we go for step 2, which is to substitute into the heat equation. Substitute into the heat equation. So, and to do that, we are going to have, of course, we know partial u of xt, partial t is the same as summation from n equals 1 to infinity now of, this is the definition. So put it into that expression up there, and that is d un cap of t dt sine n pi of x all over L. So we substitute that way. And then for the other one, we have partial squared u x comma t of partial x squared. That is summation from n equals 1 to infinity of un cap of t, then n pi over L squared sine n pi x all over L. So this is u of t now. So imagine we differentiate it twice. That's exactly what we get right there. Then now it means we have to equate this with this, right? Because that's what the original heat equation is about. This equals that. So we equate both of them. So let me see what I can use here. So let me go for this. We now have, so we say summation from n equals 1 to infinity of du n cap of t dt sine n pi x divided by L is equal to summation from n equals 1 to infinity of un cap of t n pi over L all squared sine n pi x all over L. So we have, so this is the left hand side, right? This is the left hand side, and this is the right hand side. So next we have step 3. So step 3, we solve for the coefficients. Solve for the coefficients. So by the orthogonality of the sine functions, we can isolate the coefficients for each n. So this results in a set of decoupled ODs for each un cap of t, so that we now have d un cap of t dt equals minus n pi over L all squared un cap of t, so that un cap of t is equal to un cap of 0 e raised by minus n pi over L all squared, like this. And that leads us to step 4. So step 4, we have the general solution. General solution. So the general solution for u of x, comma t is u of x, comma t equals summation from n equals 1 to infinity of un cap of 0 e raised by minus n pi over L squared t sine n pi x over L. So that gives us the general solution to the problem. Okay. So we can then apply initial condition. I mean, partial differential equations can be quite a lot. Step 5, we have to apply initial condition. So given an initial condition, u of x, comma 0 equals f of x, or let me write that out more clearly. Given an initial condition, u of x, comma 0 equals f of x, we use the Fourier sine series expansion to find un cap of 0. So the Fourier coefficients un cap of 0 are computed by projecting the initial condition onto the sine functions. So we have un cap of 0 equals 2 over L, integral from 0 to L, f of x sine n pi x over L dx. And then that takes us to step 6, quite a lot. Step 6, but we are getting to the end. So step 6, here we have the final solution. Final solution. So thus, the solution to the heat equation is u of x comma t equals summation from n equals 1 to infinity of 2 over L integral from 0 to L f of x sine n pi x all over L dx. All of this multiplied by e raised power minus n pi over L all squared multiplied by t up there sine n pi x all over L. Okay, this is quite intense. This is really intense, but it is what it is, like they say, right? So with that now, it's even hard to I mean, we need to visualize this or see it in Python to make more sense of it. So we have, this is our final solution now for that heat equation. Final solution for the heat equation. All right, so as usual, we know Python makes everything make a bit more sense. So let's look at the Python implementation of this. Okay, I think it's right here. Okay. All right. Yeah, this is the Python implementation for this. So we define here, we are taking a rod of length 10, that's like we're moving from 0 to 10. Then the time duration we take like two time steps. NX is 100, NT is 100, and we do all that. So I mean, you can study this code later. You can get it on Facebook, copy it out onto your IDE and play around with it and see what happens. So I'll just go straight to this. All this definition for the Fourier thing is in line 20, I believe, and then we have trapezoid, we have they're computing the Fourier coefficient for the initial condition and all of that happening there. So by the time we run this, we end up getting, so for different time steps and at different points along the road, so the colors are coded according to the time steps like that. So that's what the spectral method is like. So it's super efficient, especially when the equation type is right for it. Okay. So you want to study, it's quite a tedious thing. And the fact is that you can have it in other form. You can have Chebyshev, you can have Legendre. This is just for Fourier. This is just for Fourier, and it's this serious. Um, I'm not sure which will be simplest. I guess Fourier should be the simplest. I suspect it should be like that. So we've seen the whole steps and we've seen the code. In conclusion, right, the solution to the heat equation is expressed as a sum of decaying modes, each corresponding to a different frequency n. So spectral methods are efficient for problems with smooth solutions because they can represent the solution with high accuracy using a relatively small number of terms. This method is particularly advantageous when high accuracy is needed without requiring a fine grid, making it highly effective for problems in computational physics, fluid dynamics, and engineering. In fact, in the next video, I'll be comparing the three methods. I'll be comparing finite difference methods, finite element method, and spectral methods, just going through that and see which is better in which situation. Okay, so let me, let's go for let's take some practice questions. All right. So let's take this practice questions. So solve the following heat equation. Solve the following. This is like number one. Solve the following heat equation using the Fourier spectral method. So that's partial u, partial t equals partial squared u, partial x squared. 0 is less than x is less than 1. T is greater than 0. And then we have u of x, comma 0 equals x into 1 minus x. I'm going to try this. Then let me get another one that is not Fourier. Okay, let's do this. Okay. Um, 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 um. Okay, let me leave it at just this one and stop there. Okay. So if you have subscribed to this channel, thank you very much. If you have not, go ahead and do that, because in the next video I'll be comparing these three methods and see, and I'll be solving the heat equation with each method. Like I'll show the Python codes and see how they all get around solving the problem. Then of course hit the notification bell if you have subscribed, or you have not subscribed. Subscribe and hit the notification bell so you can always get alerted each time I release a new video. Comment let me about this solution. Let me know how you go about this. And then of course comment, let me know if there's a topic you like me to teach, you a problem you like me to solve, and like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.